Hey everyone, in this video we're going to go over section 3.6, derivatives of logarithmic functions. So let's begin. If we have a logarithmic function, something of the form y is equal to the log base b of x, what that means is that b to the y is equal to x. And if b to the y is equal to x, that means the derivative with regards to x of b to the y has to be equal to the derivative with regards to x of x. Well, the derivative of b to the y is going to be the natural log of b times b to the y times the derivative of y with regards to x, and that's going to be equal to, the derivative of x is just 1. We want to solve for dy dx, so we can divide both sides of this equation by the natural log of b times b to the y, the natural log of b times b to the y, to get that the derivative of y with regards to x is equal to 1 over the natural log of b. And instead of a b to the y, I'm going to write x. And this is what we have. If we have y being equal to the log base b of x, then dy dx, y prime, is equal to 1 over the natural log of b, of the product of b and x. And in particular, if b is equal to e, then we have the log base b of x being equal to the ln of x, and we have the natural log of e being equal to 1. So we can rewrite, if y is equal to the natural log of x, then y prime is equal to 1 over x. So these are our two new derivative formulas, if you want to think of them that way, that we're introducing in this section. The derivative of some logarithmic function is 1 divided by the product of the log of the base times x. So let's use these on this example. Example 1. We want to differentiate y, which is equal to the natural log of x cubed plus 1. So we're going to take the derivative of y is equal to the natural log of x, but in this case we have y is equal to the natural log of x cubed plus 1. We're going to have to use our chain rule. So y is equal to a composition of functions where f of x is equal to the natural log of x and g of x is equal to x cubed plus 1. That means f prime of x is equal to 1 over x, and g prime of x is equal to 3x squared. Well, that means y prime, which is the derivative of this thing, is equal to f prime of g of x times g prime of x, or we get f prime, which is 1 over g of x, x cubed plus 1 times 3x squared. Or we could say y prime is equal to 3x squared divided by x cubed plus 1. Perfect. Well, take a look at what we have over here. So for all of these natural log functions, we'll do this down here. Any function of this form is of the form y is equal to the natural log of g of x. We already know what f of x is. F of x is, for problems like this, is always going to be the natural log of x. So if we wanted to come up with a generalized formula for equations of this form, well, y prime is going to be equal to, we're going to get the derivative of natural log of g of x is 1 over g of x times the derivative of the inside, g prime of x. Or we could condense this down and say that if we're taking the derivative of something of the form y equal to the natural log of g of x, then y prime is equal to g prime of x divided by g of x. So, a special case of what we've done over here involving the chain rule. Let's use this to find the derivative. We'll, for example 2, we'll find the dx of the natural log of the sine of x. So, what we have is something of this form. Y is equal to the natural log of g of x. We have y is equal to the natural log of a sine of x. So we get g of x is equal to the sine of x, and g prime of x is equal to the derivative of sine of x's cosine of x. The formula on the back says that the derivative with regards to x of the natural log of a g of x is equal to, by our chain rule, 1 over g of x times the derivative of the inside, which is g prime of x. So for this problem, the derivative with regards to x of the natural log of the sine of x is equal to sine of x below the derivative of sine of x, or cosine of x. Cosine of x divided by sine of x can be called the cotangent of x, though I'd give you credit for that too. So, like I said, this is just what we're doing here. This derivative of the natural log of g of x is just a special case of here. For a third example, we have f of x being equal to the square root of the natural log of x. Well, this is once again a chain rule. I will go through, and instead of a lowercase of f, I'll use a capital F, so I can keep with this notation of capital F of x being a composition of little f of g of x, where f of x is equal to, we can call it the square root of x, but for what we're doing it'll be more convenient to call it x to the 1/2, and g of x is equal to the natural log of x. We're going to use the chain rule. We need the derivative of f of x, of little f of x, f prime of x. By that power rule, the exponent's going to come down. We get 1/2 of x to the 1/2 minus 1 is negative 1/2. And we need a g prime of x, which is 1 over x. So by the chain rule, this thing, f prime of g of x times g prime of x, what that says is the derivative of the square root of the natural log of x, I'll call f prime, capital F prime of x, is equal to 1/2 of g of x, which is the natural log of x, to the negative 1/2 all times g prime of x, which is 1 over x. Oh, it'd be good form. You could call this thing 1 over 2x times the square root of the ln of x. Really, I'm just combining that 1/2 with that 1 over x, and wherever you want to put that, that's fine. So, same thing. This is the chain rule with the power rule. This is the natural log of x all to the 1/2. From last time we were talking about the chain rule with the power rule. we brought our exponent down, the inside stayed the same, we subtracted 1 from the exponent, and then we multiplied by the derivative of the inside. This last step is just gathering like terms. Let's see what example 4 is. Okay. Example 4 wants us to differentiate. They want us to find f prime. We don't need that anymore. Well, we'll find f prime of x if f of x is equal to the log base 10 of 2 of the quantity of 2 plus the sine of x. Well, we know that if f of x is equal to the natural log, not the natural log, the log base b of x, then f prime of x is equal to 1 over the natural log of b times x. In this problem, we have b being equal to 10, but we're going to have to use a chain rule. We have to use a chain rule because we have this 2 plus the sine of x floating around. So, f of x, if f of x is equal to the log base 10 of 2 plus the sine of x, then f prime of x has to be equal to 1 over the natural log of b, ln of b, which is 10, times the inside, 2 plus the sine of x. All this is being multiplied by the derivative of the inside. The derivative of 2 is 0, plus the derivative of sine is cosine of x. All that's over 1. So we can combine everything together. F prime of x is equal to the cosine of an x divided by the natural log of 10 times 2 plus the sine of x. So, using our formula, had a chain rule here. We had a composition of functions. We composed the log base 10 of x with 2 plus the sine of x. If we sticking with the notation, I would have to go through and change all of these f's to capital F's. This one, and that one. So we can say capital F of x is equal to the composition of little f with g of x. And we call this f of x, and we call this g of x, and we would proceed with our chain rule. F prime of x is equal to 1 over, well, that thing, ln of 10 times x, and g prime of x is equal to the cosine of x. And we could go through, fill out our chain rule. You guys don't have to go through and fill out these steps every time. You can kind of take them, take on your parts as you get to them. Really the big takeaway here is that we're taking derivatives of log functions. Let's see the next example. So for example 5, we're going to start on using some identities. And before we begin with example 5, let's go over kind of our 3 big log rules. For any base, any b greater than 0, the log base b of a times b is equal to the log base b of a, and I'll call that c, just so they're different, plus the log base b of c. So we have log base b of a times c is equal to log base b of a plus log base b of c. The log of the product is equal to the sum of the logs. the log base b of a divided by c is equal to the log base b of a minus the log base b of c. The log of the quotient is equal to the difference of the logs. And log base b of a with an exponent of c, well, exponents come out front as coefficients, turn into c times the log base b of a. These are our three kind of main log rules, and we will start to use them, or you're free to use them, especially if we wanted to take the derivative with regards to x of, I lost it, there it is, the natural log of x plus 1 divided by the square root of x minus 2. So, two different ways we can solve this problem. One is, well, we know that the derivative of the natural log of x is 1 over x. We got to use a chain rule here. We have this thing, f of x being equal to the composition of f with g of x. We have f of x being equal to the ln of x. And we will say, I don't have space over there, g of x being equal to x plus 1 over the square root of x minus 2. That means f prime of x is equal to 1 over x, and g prime of x, by the quotient rule, call that x plus 1 divided by x minus 2 to the 1/2 is equal to low x minus 2 to the 1/2 times the derivative of the top, which is just going to be 1, minus the top, which is x plus 1, times the derivative of the bottom, which is a chain rule again, 1/2 of x minus 2 to the negative 1/2 times the derivative of the inside, which is just 1, all over the denominator squared, x minus 2 to the 1/2. Cleaning this up a little bit, we get g prime of x being equal to x minus 2 to the 1/2 minus 1/2 of, we'll call that x plus 1 times x minus 2 to the negative 1/2 all over x minus 2. And I wrote that poorly. That's supposed to be all over x minus 2 to the 1/2 quantity squared. X minus 2 to the 1/2 squared is just over x minus 2. So we get g prime. Okay, the final step, filling out our chain rule for this thing, we get that the derivative with regards to x of the natural log of x plus 1 divided by the square root of x minus 2 is equal to, so now by our chain rule we do 1 over the inside argument, x plus 1 over the square root of x minus 2 times the derivative of the inside, this thing, x minus 2 to the 1/2 minus 1/2 of x plus 1 times x minus 2 to the negative 1/2 all divided by x minus 2. We need some parentheses and a longer bar. Didn't save myself enough space there. But this is following the formula that the derivative with regards to x of the natural log of a g of x is equal to g prime of x divided by g of x. So what we have here is just our g of x is this thing. And we could go through and we could simplify this, but I want to go through and show you a different way. Well, the derivative with regards to x of the natural log of x plus 1 over the square root of x minus 2 is equal to the derivative with regards to x of, using our log rules, the natural log of x plus 1 minus the natural log of the square root of x minus 2, which is equal to the derivative with regards to x of the natural log of x plus 1 minus, and you know how we call the square root of x minus 2 to the 1/2? Well, our log rules say that exponents can come out as coefficients. So this is equal to the derivative with regards to x of the natural log of x plus 1 minus 1/2 of the natural log of x minus 2. Derivatives distribute over addition and subtraction, equal to the derivative with regards to x of the natural log of x plus 1 minus, constants can come out in front of derivatives, 1/2 of the derivative with regards to x of the natural log of x minus 2. Now we can take these derivatives. This is equal to 1 over x plus 1 times the derivative of the inside, which is just 1, minus 1/2 times 1 over x minus 2 times the derivative of the inside, which is just 1. And if you go through the work and put everything up here on a common denominator, this x minus 2 is going to cancel out. This will reduce to this. But this is why we're exploring logarithmic differentiation, is you have a lot of ability to break apart functions using logs. And you can turn a derivative that could be otherwise fairly painful and tedious. I would actually go a couple more steps with this, into something that's quick and easy. Let's see. That's right. So, example 6. Perfect. Let me take care of something. So example 6. We have f of x being equal to the natural log of the absolute value of x. And we want to calculate the derivative of f of x. Well, so we're going to have a chain rule. We're eventually going to have to deal with this derivative of the absolute value of x. And remember that, so the absolute value of x is equal to x if x is bigger than or equal to 0, and negative x if x is less than 0. That means the derivative with regards to x of the absolute value of x is 1 if x is bigger than or equal to 0. Really, you don't have or equals there. If x is bigger than 0, it's 1, negative 1 if x is less than 0, because the absolute value of x is not differentiable at 0. Okay. So when we go to take the derivative of this function, f prime of x is going to equal 1 over the absolute value of x times the derivative. So either times, so we'll say this. F prime of x is equal to, we'll say 1 over the absolute value of x if x is bigger than 0, or negative 1 over the absolute value of x if x is less than 0. Okay, but let's explore this a little bit more. If x is positive, the absolute value of x is just x. So we get 1 over x if x is bigger than 0. Because if x is positive, the absolute value of a positive number is just that number. But if x is less than 0, this is equal to negative 1 over negative x if x is less than 0? Well, negative 1 over negative x, those minus signs cancel out, and if you look, f prime of x is equal to 1 over x if x is different than 0. It's not defined if x is equal to 0. So that's a neat result in my opinion. F of x is equal to the natural log of the absolute value of x, and its derivative is 1 over x. We'll use this a lot of times this gets used going the other direction. In chapter 5, when we start chapter 5, we're used to derivatives taking equations in one direction, and we'll do antiderivatives to go in the other direction. So logarithmic differentiation, that's what this section is all about. I want to rewrite those log rules again. We got the log base b of a times c is equal to the log base b of a plus the log base b of c. The log base b of a divided by c is equal to the log base b of a minus the log base b of c. We've got the log base b of a to the c is equal to c log base b of a. And we have if f of x is equal to the log base b of x, that tells us f prime of x is equal to 1 divided by the natural log of b times x, not b to the x. Or a special case of this, if we have a g to x is equal to the natural log of x, that tells us g prime of x is equal to 1 over x. These are kind of our 5 big pieces that are floating around in this lesson. What we're going to use them for is we're going to use them to simplify derivatives. Kind of like we did in this example, how we could have done 1 over the inside times the derivative of the inside, and we got this big quotient rule, and we would have had to simplify. What we did over here was we used our log rules and we spread everything out, and we took the derivative of the parts. So the process for logarithmic differentiation is to help us take derivatives of big things like y is equal to x to the 3/4 times the square root of x squared plus 1, all divided by 3x plus 2 to the 5th. And what we're going to do is we're going to calculate y prime. Now, without using logarithmic differentiation, the technique I'm about to show you, you guys are completely equipped to do this. You can do this. You can first apply your quotient rule. You do low times the derivative of your top. The derivative of your top is a product rule with an embedded chain rule in it. Low times the derivative of the top minus the top times the derivative of the bottom, another chain rule, all divided by the denominator squared. And you'd be done. Easier said than done, but that's all you have to do. So this boils down to the fact that if this side is equal to that side, then I can take the log of this side and have it equal to the log of this side. And it doesn't matter if we take it doesn't matter for what positive value of b I pick. So I'm gonna pick the log when b is equal to e. And instead of the log base e of x, I'm going to write the natural log of x. The reason why is simple. Logs and natural logs, they behave the exact same way. They're the exact same thing. It's just the base is included in natural log of x. So I always use the natural log of x because it's faster to write. There's honestly nothing more to it than that. It's just faster to write natural log of x, but we could take the log base whatever we want of either side. So like I said, I'm going to take the natural log of x. what that means is, I'm going to take the natural log of both sides. So what that means is I get the natural log of y is equal to the natural log of this thing, x to the 3/4 times the square root of x squared plus 1 divided by 3x plus 2 to the 5th. And now, by our log rules, this is equal to, we get the numerator, ln of x to the 3/4 times the square root of x squared plus 1 minus our denominator, the natural log of 3x plus 2 all to the 5th. Now, I'm going to break this up at multiplication equals natural log of x to the 3/4 plus natural log of, and I'm going to call that x squared plus 1 to the 1/2 minus the natural log of 3x plus 2 to the 5th. Last step is to bring out all of our exponents as coefficients. So we get the natural log of y being equal to 3/4 times the natural log of x plus 1/2 the natural log of x squared plus 1 minus 5 times the natural log of 3x plus 2. Perfect. So now we have at least simplified the way it looks. And now, if these two sides are equal, that means the derivative with regards to x of y has to be equal to the derivative with regards to x of this whole side. 3/4 natural log of x plus 1/2 natural log of x squared plus 1 minus 5 natural log of 3x plus 2 bracket. Okay, so now we're going to have to apply our chain rule. Y is a function of x, so the derivative with regards to x of, the natural log of y, that natural log, I forgot to copy it down when I went here, the derivative of the natural log of y is equal to 1 over y times the derivative of y with regards to x. That's our chain rule. That's going to be equal to derivatives distribute over addition and allow constants to pass through. So this first term will become 3/4 times 1 over x plus 1/2 times 1 over x squared plus 1 times the derivative of the inside minus 5 times 1 over 3x plus 2 times the derivative of the inside. Cool. So our left-hand side I'm just going to leave as 1 over y dy dx. That's equal to 3 over 4x plus, this 2 is going to cancel out with that 2. We get x over x squared plus 1 minus 3 times 5 gives us 15 over 3x plus 2. What we want to solve for is this dy dx. We've got this y on the left-hand side, or 1 over y. If I multiply on the left by a y, I can multiply on the right by a y, and we get dy dx is equal to 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2 times y. But we know what y is. Y is this thing. X to the 3/4 square root x squared plus 1 over 3x plus 2 to the 5th. We're done. Stop at this point. I would strongly discourage you from manipulating this thing, trying to put things on common denominators and gather like terms. Just leave it alone at that step. Okay, so we did some steps here. We were given an equation. The first thing we did was we took either the log or the natural log of both sides. Like I said, I take the natural log because there are less letters to write, but it doesn't matter which log we use, they all behave the same. So I took the natural log of both sides, and then I use log rules to separate. Then what we did, so we separated, then we did an implicit derivative. We did implicit differentiation. After we did implicit differentiation, well, kind of a part of implicit differentiation is solve for y prime. So really the only thing we're doing, we're taking implicit differentiation, something that you guys know now, and we're just taking the log of both sides of an equation to help accordion things out. This is a powerful tool for things that are incredibly difficult to take the derivative of. This thing over here, we could have tackled with the quotient rule. I'm not going to. Maybe if I was in class and I had a whiteboard, but that thing would just get kind of big. If we have functions, this will be example 8. We could have f of x being equal to x to the square root of x. So, and I'm trying to see, that's fine. So, this is what we have. If we're trying to take the derivative of this, we don't have anything that allows us to kind of tackle functions of this form. But if we call y x times the square root of x, well, that means the natural log of y has to be equal to the natural log of x to the square root of x. Well, that means the natural log of y has to be equal to the square root of x times the natural log of x. So, when we go through to take the derivative of this, we get 1 over y times y prime is equal to the derivative of our first times our second plus our first times the derivative of our second. Now we want to gather our like terms. I'm just going to copy this on the page behind us, or behind. 1 over y prime equals 1/2 of x to the negative 1/2 times the natural log of x plus x to the 1/2 times 1 over x. So that just copies it from the back page. We'll simplify. 1 over y prime is equal to, I wouldn't do much to that aside from call it 1, I'd probably call it 1/2 of the natural log of x times x to the negative 1/2 plus x to the 1/2 divided by x is x to the negative 1/2. Now we want to solve for y prime. We want to get it all by itself. We need to multiply both sides of this equation by y. You need those parentheses. These y's will cancel. We're left with y prime being equal to 1/2 of the natural log of x, x to the negative 1/2, plus x to the negative 1/2 times y, which for this problem was x times the square root of x. So, not implicit differentiation, we use implicit differentiation. Logarithmic differentiation allows us to take derivatives of things that are difficult. When we have x's in a base, when we have x's up in an exponent, if we just can't find a way to break apart something to take a derivative of it, try and use logarithmic differentiation. Allows you to take the log of both sides of an equation, and our log rules are powerful. There's a lot of manipulation we can do when we remember our big three log rules. So we brought an exponent down out front. We then took the derivative of both sides. At this point we did a dx. I didn't write it, but that's what we were doing. And it's bad form to put your dx on the right hand side. This should definitely come out front. So if these are equal, that means these are equal, that means these are equal. This is implicit differentiation. I ran out of space, so I just rewrote what I had on the back side. We had a 1 over y. We wanted to get y prime by itself, so we multiplied both sides of this equation by y. We got y prime was equal to this thing times y, which, for this problem, y was equal to x square roots of x. So, implicit differentiation is a strong tool. So I've got a derivation for you now. Let's talk about the number e. We're going to talk about e as a limit. Okay, so if we have f of x being equal to the natural log of x, then we have f prime of x being equal to 1 over x. So f prime of 1 is equal to 1. But now let's use the limit definition for the natural log of x. We know that f prime of 1 is equal to the limit as h goes to 0 of f of 1 plus h, the natural log of 1 plus h, minus the natural log of 1, all over h. Okay, well, the natural log of 1 is equal to 0, so we can call this the limit as h goes off to 0, and I'm going to, instead of dividing by h, multiplying by 1 over h times the natural log of 1 plus h. Well, coefficients can be risen up to exponents. So this is equal to the limit as h goes off to 0 of the natural log of 1 plus h all to the 1 over h. Perfect. And this, because we know, has to be equal to 1. So this result really is at the limit as h goes off to 0 of the natural log of 1 plus h to the 1 over h is equal to 1. So now let's do this. Let's take the number e. E is the same as e to the 1. But by this identity, that's equal to e to the limit as h goes off to 0 of the natural log of 1 plus h to the 1 over h. Which, by continuity, we can pull that limit out here. This is equal to the limit as h goes off to 0 of e to the natural log of 1 plus h to the 1 over h. But this identity, this will cancel out, and we're left with the limit as h goes off to 0 of 1 plus h to the 1 over h. Perfect. And now if you look what this says e is equal to the limit as h goes off to 0 of 1 plus h over 1 over h. And in fact, it's a lot more common. If we let n be equal to 1 over h, then as h goes to 0 from the right, then n goes to positive infinity. And we can rewrite this limit as e being equal to the limit as n goes off to infinity of. So if n is equal to 1 over h, that tells us that h is equal to 1 over n, and we get 1 plus 1 over n all to the n. And this is another way that we can define the letter e. This is approximately equal to about 2.7. Another interesting way e keeps on showing up in mathematics. So this is really logarithmic differentiation. The book didn't have too terribly many examples in the section, so let me do a mad scramble to find one more for you. 3.6. Let's find an even problem. Let's do. They really don't give you a lot of good ones to break it apart. 1 second. Perfect. So one more example just to drive the concept home. This is going to actually be 40 out of the homework. It says y is equal to e to the negative x times the cosine squared of an x, all divided by x squared plus x plus 1. This thing, you guys could take the derivative of it with the quotient rule. It just has a lot of moving parts. I would recommend you use logarithmic differentiation. The book also tells you to use logarithmic differentiation for this problem. So what that says is, if y is equal to that thing, that means the natural log of y has to be equal to the natural log of that thing. E to the negative x cosine squared of an x all over x squared plus x plus 1. And you know, I'm going to take that e to the negative x, and I'm going to move it to the denominator. We get a cosine squared of an x divided by an e to the x times an x squared plus x plus 1. So now, that means when we take the derivative with regards to x of the natural log of y, that has to be equal to the derivative with regards to x of the natural log of this thing. Cosine squared of x all over e to the x times x squared plus x plus 1. But we can use some log rules to break this up. This is going to be equal to the derivative with regards to x of, we take our numerator, the natural log of the cosine squared of an x minus the natural log of our denominator, e to the x times x squared plus x plus 1. But that's equal to the derivative with regards to x of, this squared can come out front, and we get 2 times the natural log of the cosine of x minus the natural log of e to the x. And now this minus sign is going to distribute minus the natural log of x squared plus x plus 1. So we can say, and we'll say that, we'll do one more, the derivative, and that'll be equal to the derivative with regards to x of 2 ln of cosine of x minus x natural log of e minus natural log of x squared plus x plus 1. Perfect. So if that derivative is equal to that derivative, then by implicit differentiation, and I'll write this here, d dx of natural log of y, what that says is 1 over y times the derivative of y has to be equal to, derivatives distribute over subtraction, we have 2 times 1 over the cosine of x times the derivative of cosine, which is a negative sine of x, minus, so x ln of e, the natural log of e is 1, so minus x just becomes minus 1, and then we're going to minus the derivative of the natural log of x squared plus x plus 1 is equal to 1 over x squared plus x plus 1 times the derivative of the inside, 2x plus 1. At this step, I would highly recommend you guys just rewrite what you have. 1 over y prime is equal to a sine divided by a cosine is equal to a tangent, and we get a negative 2 times a tangent of x minus 1 minus 2x plus 1 over x squared plus x plus 1. Final step is to solve for y prime. Multiply on the left by a y, multiply on the right by a y. Don't forget we know what y is equal to. What that tells us is y prime is equal to negative 2 times the tangent of an x minus 1 minus 2x plus 1 over x squared plus x plus 1. All that is times y, which is e to the negative x cosine squared of an x all over x squared plus x plus 1. And that's it. That is our beautiful derivative for that thing. Go and figure out where that thing's horizontal, everybody. For homework, what I want you to do, and I'll stop moving it so you're watching this on YouTube, you can pause. Go off, do 3 through 23, every other odd, and then go and do 39 through 51 odd. All your implicit differentiation is in over here. I keep on calling it implicit differentiation because that's what we're doing. We're using log rules to break apart an equation, and then we're using implicit differentiation. Let me know if you guys have any questions. Let me know if you want to see any more examples of any of this. Shoot me an email, and I'll see you guys next time. Have a good day.